All right, before we get started, how are you prepared for the exam?
I have 3 exams. Yeah.
Yeah, a lot of us have three.
Yeah.
Not well.
Oh, yeah.
What you're gonna hear.
It'll be interesting.
The focus for analysis comes after tomorrow when I'm going to evaluate what is done.
Right.
So, do you want to move it to Monday?
Yes.
Could be.
Yeah.
Actually.
I mean, I don't mind.
If this
I
is a
would-
possibility,
Yeah.
oh, y'all, I'll take it.
What did she say?
If it's early, I'll take it Monday.
Okay, so here's what I usually do. If everybody in the class does not mind moving it to Monday, I would move it because it was on the schedule for Friday. I want to ask, does anybody in the class wants to take it on Friday? Then maybe I'll allow them to take it on Friday and the rest of the class can take it on Monday. I can do that. So please, all of you, put your head down. And then, yeah. Which one of you want to take it on Friday? Don't pick. Who's in the class want to take it on Friday? Oh, wow. Okay, then we're doing it all of you on Monday. Yay, good job. I don't mind. All right, you guys, you can study and do well.
Thank you so much.
You're welcome. I'm a mother and you're all my children.
Her Halloween gift is a couple extra days to study.
The Halloween gift, I'll bring you chocolate while you're taking the exam.
Sweet.
All right, so that you'll do well while eating sweets. Okay, so let's get started. All right, so what are some applications of IR spectroscopy? Yes, Rachel. Modification? Quantification, yes. Kristen? Identification, Grant? Structural elucidation, so chemical composition, all of that. Quantification, chemical composition, identification, structure elucidation, all of that. Okay, so that's great. You missed the fun.
Little bit. I'm here for most of it.
What's that?
I'll catch.
Well, the
90%.
fun was we're moving the exam to Monday.
That is fun. I thought I was like on the hot seat.
Never change, homie, never change.
All right. Okay. What type of energy is absorbed in IR spectroscopy? Remember the types of energy? What types of energy? Electronic? And?
And, rotation,
Yeah, so which one in IR?
I don't know.
Good. Go ahead, Kirsten. Yeah. Vibration, yes. Electronic, remember this. Both atoms and molecules absorb electronic because it is from the electron. So you have to remember the electrons of the valence electron. But vibration is only for molecule, rotation is only for molecules. So the IR radiation is for vibration. It's within the range of vibration. UV vis is electronic. Okay. Is MIR or mid-infrared for milk composition, just random determination, a primary or secondary method? We talked about this last time. Is it a primary method or a secondary method? It's a secondary method, Albert. Why do you think it is? Exactly. So the naming of primary and secondary is only meaning that the secondary method needs calibration. And the way we calibrate it is using official methods of analysis, these are the primary methods. So secondary methods need calibration, and MIR or IR in general, all of them need calibration using primary methods of analysis. Okay, so in IR and in mid-IR, we have two types of instrument. The first one is this dispersive instrument. And with dispersive, I mean the dispersion of light, the dispersiveness from the entire light into singular lambdas. And so this happens when there is a monochromator in there, and the monochromator disperses light, and then it basically one lambda, one wavelength reaches the sample and gets absorbed. So the components of the instrument are exactly the same as the regular UV vis spectrophotometer, and usually it's double beam. Do you remember what double beam means? Yes, Kristen? It's split where part of it goes to a reference cell and part of it goes to your sample, and your reference cell is your blend. Okay, perfect. So radiation source and detectors, these are FYI. I will never ask you what type of detector is there in a dispersive instrument, but it's FYI here. However, it's very rare you find now dispersive instrument. Most of them are called Fourier transform, which it references a complicated mathematical equations to convert or to analyze the radiation and convert it to kind of something that you can quantitate with. Okay, so Fourier transform is the most common instrument, like FTIR, Fourier transform IR, infrared. So you probably heard of FTIR. Okay, so what's in Fourier transform equipment? The radiation is not dispersed. So we don't have a monochromator. All the light reaches the sample, and then you end up having a spectrum. So you will have lots of absorbance at different wavelengths. And if you remember, some of you might remember that I said thus light interference, we'll hear again in the IR lecture. Okay. No. The light interference is, if you remember this image, I showed it at the beginning of introduction to spectroscopy and the interaction of light and matter. And in here, what they do is there is an interferometer where the IR radiation gets split before it gets to the sample. And then it gets recombined in a way that either you amplify the intensity of light or you cancel it. And in this way, because vibration energy is really smaller than electronic energy, it kind of enhances the sensitivity, because the energy is very low compared to electronic energy. So in this way, they can amplify the intensity of light, or they can cancel interference. So the design is in such a way that we can remove interference and enhance sensitivity. And in this kind of instrument, there is a lot of, all the data is acquired as spectra, and then it's very quick, and we kind of reduce the signal to noise ratio by employing this amplification and cancellation. Okay. A lot of words here. I'm going to tell you what I want you to remember. Transmission IR, light goes through the sample, and you measure transmitted light that comes out of the sample. So as the word implies transmission. So light goes through and gets transmitted. And usually it's for liquid samples. Light goes through the liquid and transmitted light reaches the detector. Sometimes you can use it for solid if you mix it with mineral oil, disperse it in mineral oil, or grind it and form a pellet with potassium bromide. So it's not very common, but what I want you to remember is not how you grind the solids and pellet it and what you pellet it with. What I want you to remember is transmission IR, you measure transmitted light. Simple. The other thing I want you to know is attenuated total reflectance. So this is used for solid. So basically, you have your solid samples. So light comes down and gets reflected. Some of the light is absorbed by the particles, by the components, and the rest of the light is get reflected. So the reflected light is what gets measured, okay? So this is for solid samples. So in this type of IR, the reflected lights get transmitted. And then there's also internal reflectance used for liquid specifically, with some of the light goes through the liquid. And then once some samples or component absorb light, the light gets reflected. Okay, so what do I want you to know? Transmittance passes through, mostly for liquid, measuring transmittance. Reflectance measures the reflected light, whether for solid samples or liquid samples. Okay. So there are interfaces that you can link to FTIR or Fourier transfer IR. So you can have chromatographic separation, so your components get separated by GC, and as components leave the GC, they get subjected to IR radiation and absorption is measured, or IR spectra is collected. You can also have microscope with FTIR. So you would have your microscopic slides with a sample on the microscope, and then you project an IR radiation on your slide, and then you measure IR spectra. So quantitation, if you're using dispersive IR, that means you are using a monochromator and a single light passes, you can apply Beer's law and simple quantification. If we are using Fourier transform, it's not as simple. You do multivariate regression or principal component analysis to convert all of those light absorption spectra to meaningful quantitative and qualitative data. So the computer does it for you. You don't do it manually. So in any case, we need to calibrate. We said these are secondary methods of analysis. We need to calibrate. A very common IR application in mid-IR is IR milk analyzer. It's very common, used in the dairy industry, where quick composition of milk is determined as the milk is pasteurized, is processed. You get compositional analysis for fat, moisture, and lactose. And this is what I have in red. For fat, we're measuring the vibrational energy absorbed by the carbonyls in the fatty acid, the C double bond O. And then in protein, we measure the amine, the NH groups, the vibration of NH groups, and in lactose, the vibration of the hydroxyl groups or the OH groups. So, but everything requires calibration. Using known concentration, yes. Yes, yeah. And I put them in order: fat, protein, lactose, carbonyl, amide, hydroxyl. So Raman spectroscopy, I'm not going to dive into its specifics, but it is a common IR spectroscopy used that gives you good structural elucidation, especially in samples that high in moisture, in water, because there's no interference from water absorption. So the way it works, it's based on light scattering. So when the light reaches the different components within a sample, it gets scattered. So there is Rayleigh, I can't pronounce it well, and then Raman scattering. So one is all of the energy is scattered. So basically same energy hits, same energy is scattered. Whereas Raman, some of the energy actually get absorbed by the components, and scattered light is of a lower energy, same as principle as fluorescence. Some of the light gets absorbed and the scattered light carries less energy. That's all what I want you to remember from this. And the difference is equal to the energy that was absorbed, vibrational energy that was absorbed by the components between the light that hit and the light that got scattered. So Raman is very sensitive and it's a very powerful tool for structural characterization, especially when there is high moisture content in your sample. So laser is the source of radiation, and it can be quantitative based on complicated equations, PCA analysis, multivariate analysis. So, but you can do quantification, and you can do both solid and liquid, like I said, because water has low impact in this region or this type of spectroscopy. Near IR, so other than mid-IR, near-IR is also applied. That's the range between 0.8 to 2.5 micrometer. And this is commonly used again for composition, but mostly in solid foods. And it uses diffuse reflectance technique. So what is diffuse reflectance technique? So basically, this is the image describes it really well. So what happened to my light? Oh, there. So what happens here is we have the light coming onto a solid sample, finely ground. Some of the light penetrates and then gets absorbed, and the rest of the light that doesn't get absorbed gets reflected. And the reflected light carries characteristics of the components, because by knowing the incident light and then the reflected light, we can determine the light that got absorbed by the different components, do all of the mathematical calculations, and determine composition. So the radiation penetrates through the surface. Some of the light gets absorbed, the rest of the light gets reflected back. So that is what is called diffuse reflection. So the light diffuses in, some of it gets absorbed, the rest of it gets reflected, and that carries the identity of the components based on what they got, what they absorbed, and then we can determine composition. So sample needs to be ground finely and evenly and with a smooth surface to get repeatable results. So the peaks that we get are overtone, not as sharp as mid-IR. The peaks are like broad peaks, but we can still use the data to quantitate based on the functional groups that get absorbed. So I don't know why it's, did I lose? Oh, there. Okay, so we measure based on the hydrogen atom attached to a carbon, a nitrogen, or an oxygen. These are the common groups in water, proteins, lipids, and carbohydrates. Okay, so this is the wavelength at which we get different vibration of different function groups in water, in protein, in lipids, and in carbohydrates. And FYI, this is how they look like. It's not sharp peak, more overtone, broad peak. So this is the cheese here. So this is water, fat, protein, and then this is wheat and eggs. Typical spectra. So in these IR, you can have monochromator or interferometer, mostly interferometers. Don't worry about anything else, FYI, on this slide. And here, reflectance, diffuse reflectance for solids, transmission for liquid. That's what I want you to remember. What? Just know that you can either have a monochromator like dispersive or interferometer, same as mid-IR. Don't worry about the radiation source in the detectors. And then here, reflection for solid, transmission for liquid. And you can do qualitative determination, or you can do quantitative, but the quantitative analysis for interferometers are complicated based on multivariate regression and PCA analysis, but you can get quantification. So no Beer's law when you have interferometer is that I want you to remember. It's used widely for grains. So in flour mills, for example, they have an IR, a near IR instrument that constantly measure protein and ash. In flour samples, these are important measurements for quality for grains. Oil seeds, fat is an important measurement, quality, and protein as well. So calibration is key. This is what I want you to remember, is we need to calibrate based on primary methods of analysis. And it's also very commonly used to determine contaminants. So here, for example, infant formulas, a few years ago, there was a contamination with melamine. So this is the spectra of melamine. This is the spectra of infant formula. So if we see some peaks in the infant formula that do not belong, and they resemble some peaks in melamine, we can determine, not necessarily quantitate, but determine presence of melamine. So simple. Can we use NIR for online measurements during processing? That's the purpose of it, okay? Mostly, for compositional analysis, mostly this is done through online quality measurements. Okay. This is a list of advantages and disadvantages to review. And that ends lecture on IR. Okay. Any questions? Yes, great.
For
You lost it? Any other question? Any questions that might help Gray remember his question? Okay. If you remember at any time, tell me. Okay. All right. So we're kind of done with half of the class material. Can you believe that? Where did the time go? I was having fun. Now we're going to turn the page to a more applied part of the class where now we learn methods to actually quantitate and characterize food ingredients and products. So the first segment of this part of the course is proximate analysis. How would you define proximate analysis? What does it mean to you when you hear the word proximate analysis?
Moisture, age, protein, carbohydrate.
I just want to think it's like a kind of like a general overview of a product that kind of gives you broad information to look at for determining what you want to look at.
Exactly. This is true and this is true. Let's put them together. So proximate analysis is mainly an analysis that we do to look at the major components of your food to get an approximate idea of that food. An approximation also, all of the methods for proximate analysis are crude methods of determination. You'll hear me say crude fat content, crude protein content, because it's not an accurate method because there are inaccuracies in each of the methods we use, and then we're going to talk about these inaccuracy for each component. So the proximate analysis, what are the main components that we measure in proximate analysis? Main components. Go ahead.
Protein, fat.
Protein, fat. What were you going to say?
Moisture.
Moisture.
Carbs,
What else?
carbs.
Carbs. One more. Ash. All right. So the main components in a food is moisture, protein, fat, protein, carbohydrate, and ash. What is that ash component? What does it have in it mostly? Huh? Non-organic, but mostly what non-organic? Minerals. Okay. Yeah. Okay. So okay. So I'm going to draw a pie. And I'm going to say this is, let's say this is moisture. This is ash, fat, protein, carbohydrate. Where did I lose you guys? Of the pie, are you hungry?
Yes.
Oh. Okay, so proximate analysis, this all will add up to 100%. Okay, 100% of the pie. So the pie is divided into segments. All right, so the ash, the moisture, the fat, the protein, carbohydrate. Okay, so 100% of the composition equals the addition of all of them together to give you that total components. All right, out of these that you see there, which one of them are on the label?
Well, carbs is kind of there, but it's sugar.
So total carbs. So you have total carbs on the on the label. Part of the total carbs, you'll see dietary fiber, you see sugars, you see added sugars, but you have a total carbohydrate. What else? Okay. Fat, yeah, fat. Protein. Do you see moisture and ash? No. We don't have moisture and ash. But why? Well, I'll get to that question later. So out of the proximate composition, we see on the label the total fat, total protein, and total carbohydrate. So, but all analyses are required for nutrition labeling. Why? Huh? So people what? Know what is the food. But for nutrition label, when you want to create the nutrition label, you only really need the total fat, the total total fat, total protein, and total carbohydrate. But why do we determine percent ash and moisture? Because you will not know the answer. Oh, maybe Haley knows the answer.
Maybe to ensure it does add up to 100%.
She's close to the answer. Exactly that. We want to make sure that everything add up to 100. We never determine total carbohydrate for the nutrition label. We determine ash, protein, fat, moisture. We subtract from 100, we get total carbohydrate so that everything adds up to 100. Besides, later when we cover total carbohydrate, you will know that there's not one method that can determine total carbohydrate in a complex sample. Why? You might ask. Let's ask George students. Why do you think there's not one method to determine total carbohydrate in a complex matrix? Do you know? Do you know, Ray? So they're very complexly different. You have starch, you have dietary fiber, you have sugars. There's not one method that gets you all of these components. They're very, very different, and quantitating them requires different methods. Unless you have a juice that only has sugar in it, you can do a total carbohydrate assay. But when you have a mixture with fiber, starch, small sugars, it's impossible. Therefore, we do the easy ones, the moisture, ash, fat, protein, subtract from 100, we get total carbohydrate that we put on the label. Then we determine dietary fiber, we put it on the label. We determine total sugars, we put it on the label. Okay. So for nutrition labeling, we have to use official methods of analysis. We have to use primary methods of analysis. We cannot use NIR or mid-IR for nutrition labeling. And we're going to talk about, in this section of the class, all the official methods of analysis. So moisture, oven drying methods, we have plenty of those. Ash, the dry ashing method is an official method. You put the sample in a multi-furnace at really high temperature, incinerate all organic matter, you weigh the remaining inorganic matter. Sockless and Modiner are both official methods, but for different types of food. So when you do the lab, you will know that you will need Soxhlet for certain groups of food and Modiner for another set of food products. However, in red is important, pay attention to this. Although Soxhlet and Modiner are official methods of analysis, they are not used for labeling. What is used for labeling is the GC method that you learned during class, the same method, but not the one that you did in the lab with the semi-quantification, the one that we actually do calibration for all of the different fatty acids that could be present in your sample, actually doing calibration curve for each one of them and do an actual quantification, and then adding the all up and adding glycerol molecular weight to it to get the total fat. So this is how we do fat analysis for total fats on the label. And then protein, you can do either Dumas method or Caldwell, and you do both of those methods in the lab. And then total carbohydrate by subtraction. Yes.
We got total carbohydrate by subtraction of protein and moisture edge. So how they add like on the label, there is 14% dietary fiber, 20%.
So dietary fiber, you determine using a separate method for dietary fiber. So you just get the total carbohydrate, in this case, 37 grams, 37 grams in a serving. That is by subtraction. The total carbohydrate is by subtraction.
So I'm secondly, how they determine the dietary fiber out of the total carbohydrate?
You don't determine dietary fiber out of the total. You determine dietary fiber by its own assay.
Okay.
We're going to learn about how you determine dietary fiber, the digestion, you digest the protein, the starch. What else you digest? You remove fat, you remove moisture, digest protein, digest starch, remove those. So that is dietary fiber. So you would measure dietary fiber actually, not by subtracting. But the total carbohydrate includes dietary fiber, if you have starch in there, you have sugars or disaccharides are all in the total carbohydrate that you get us.
Okay, so out of total carbohydrate, we can do individually class.
Exactly, individual. You can measure glucose or sugars individually. You can measure dietary fiber individually. You measure starch individually, but you don't report starch. Yeah, very good. Good question. Okay, so total carbohydrates by subtraction. That's how we determine total carbohydrate that goes on the label. Okay, any questions about proximate analysis? So there's two things. Sometimes you say proximate composition. So the proximate composition means the ash, fat, protein, carbohydrate, and fat. Proximate analysis are the methods of analysis we use to determine proximate composition. Okay. So proximate composition are actual components. Proximate analysis are the methods we use to determine the different components. So in this class, we're going to learn about the proximate analyses that we use to determine the proximate composition. Did I lose you? Ray, did you remember your question?
No.
Okay.
Put him on the spot. I'll get there.
Just checking. All right, let's see what you remember. Protein content, or what you know. Protein content and water activity are interchangeable terms. What did I say? I love proteins. Moisture content and water activity. Glad some of you are listening. Are interchangeable terms. All methods for determining moisture content are based on evaporating moisture and measuring dry matter. Moisture content is an accurate indicator of perishability. Go for it, Emmeline. H, none of the above. Anybody with different answer? You agree? Okay, Griffin, you agree. It's none of the above. So moisture content and water activity are different. We'll talk about them. And we have infinite number of methods for determining moisture content. Not all of them are based on evaporating moisture. And moisture content is not an accurate. What is an accurate water activity? What is an isotherm? You covered that in food chem, right? So what is an isotherm? Which one of those? Yes, it's all of the above. Okay, and it is a relationship between moisture content and water activity. We used to plot isotherms in lab by determining moisture content and water activity at different relative humidity. It was very extensive and lengthy lab, so we eliminated it. But you could have learned a lot from it, but it was too extensive. So yes, all of the above. Now, what's the analysis of moisture? No, what's the definition? I'm tired. What is it today? Monday. Okay, what's the definition of moisture analysis? What is it? When you say moisture analysis, what are we analyzing?
The content.
Okay, so determination of water content is one. What else? It is in the previous question.
Also, how available the water is.
So determination of water activity. So when we say moisture analysis, we don't necessarily mean only moisture quantification. So it's determining moisture content and water activity of a food gives you the complete moisture analysis. So what is the difference between water content and water activity? Yes. The water activity measures the amount of bound water. Okay. So does any of you remember Ted Labuza? Ted Labuza, if he were with us today, he would be very unhappy with this answer. It is true, but he wouldn't like to have you frame it. He's the godfather of water activity.
The water activity, I don't know if Ed would like it described as the pressure of water vapor in the food over the base pressure of water.
Exactly. Exactly. And this represents the water. Yes, because it's the water available for reactions, chemical reaction, microbial growth, and such. It's non-bound. Huh?
Can Tyler repeat it?
Wait a sec, it's coming. It's right there. Right there. You don't have it on your side?
No.
Ah. Oh, I wanted you to think about it. Okay. You can take a picture of it if you want without me in it. Okay. So moisture content is really the total quantity of water not chemically bound. So there is water that interacts with the constituents, and there's water that is chemically bound. What's the difference? So water that is chemically bound is water, the OH and H groups within chemically bound, covalently bound to the components of food. Whereas the bound water is just water interacting with sugars or salt or protein via dipole-dipole interaction or hydrogen bonding, but not chemically bound, not covalently bound. Okay, so water content or moisture content is the total quantity of water, free water that is not interacting, and the water that interacts, but not the chemically bound. And I will give you examples to differentiate the chemically bound. Okay. So the dry matter that remains after water removal is called your total solids. And total solids are important because sometimes you want to compare food samples in their protein content, in their fat content, in their ash content without the factor of water. Because different food samples have different moisture content, so moisture does not carry energy or calories. And if you want to compare different foods and the amount of protein or fat or carbohydrate they give, we have to look at them on dry basis, meaning we need to determine the dry solids and determine the fat content relative to that dry solid and the protein content relative to the dry solid, and so on, so that we can compare irrespective to the amount of water in the sample. So that's why in many places, we're going to talk about calculation on dry basis. So in your lab reports, you will be calculating on wet basis and on dry basis, because calculating on dry basis is very essential when we don't want to consider moisture in comparing foods of different moisture content. Okay. So water activity is basically a range from 0 to 1, because it is the ratio of the pressure of water in the atmosphere above the sample to the pressure of water, of pure water. So if you have pure water, the ratio would be 1, same pressure above the sample, above the water, for the pressure above the pure water. So it is 1. And relative humidity is the percentage. So at equilibrium is important because if we want to determine relative humidity, it has to be equilibrated. The environment has to be at equilibrium. Is a percentage. So relative humidity is a percentage, and it ranges from 0 to 100%. Water activity ranges between 0 to 1, and it is the equilibrium relative humidity by 100, because relative humidity is a percentage. Okay, good. So before I let you guys go, tell me the importance of moisture analysis, whether it's moisture content or water activity. Why is it important? From now on, when we learn about analysis of different components, I'm going to always ask you, why is it important in food analysis, in the food industry, in the food world? Why do we care? Great.
So you can turn the shelf life.
Shelf life. It's important for shelf life, so we need to determine at which water activity your sample is the most stable from chemical reactions or for microbial growth. It's definitely moisture is a quality determinant. So is it going to be a soggy or a firm?
Determining total carbohydrate.
Yes. Thank you. Yes, absolutely. What else can you think of? So standard of identity. For example, milk, what is the percentage of water in milk? Do you know this? Do you study this anyway? Huh?
5%.
Oh, if you say it's the remaining, people are going to cheat and put water in milk. It's not a remaining. It is 87. No, it's about 87 to 88. That's the maximum range that you can get. So if you have 90% water in your milk, what do you think? They added water. They added water to the milk, diluted the milk down. So it's a measure of standard of identity and also quality of your product. So cheeses, different types of cheeses, you will learn when we do moisture next week. You will learn that different types of cheese. Are we doing moisture this week? Parmesan cheese like this Monday, on Wednesday will be cheddar cheese. They have different moisture content. They have different standard of identity. Okay, what else? Okay, I ran out of time. Let me show you. Okay, quality factor, preservation. Oh, the one thing we didn't mention, many times we kind of dry things down to kind of ease for transportation. So non-fat dry milk transports better than the whole milk, for instance. Required for nutrition labeling. And we did talk about dry weight and the importance of determining moisture, so we can determine dry bases and compare across different foods. All right. That's it. So the exam is on Monday. Good job. All right, thank you. I'll see you Friday. What else? Wednesday. I'm out of it today.
So this week.
Okay.